Thank you, Mr. Chairman. Good morning, everybody. So the purpose of my talk is about fracture in brittle multilayer flexible substrate. So this is a part of the PhD of Joel Martello and Ian Becci. So as you certainly know, when you use glass, you often functionalize the surface to modify the property of your material. For example, to have a control of temperature, photovoltaic effect, or to have a glass that becomes transparent or compact by just playing on the electric field you impose in the layer, or you can have also a anti-reflection property for your glasses. But since a few years, the development of flexible electronic or flexible photovoltaic leads to new questions about the mechanical stability of those hard coatings when you want to deposit them on a flexible substrate. So the problem in this deposition of hard coating on flexible substrate is that there are many relevant parameters. So you can deal with adhesion problems, thickness, plasticity, and residual stresses. So to investigate this problem, we use roll-to-roll deposition techniques on flexible ETFE. This is a big device somewhere in Germany. And we deposit silver layer in between two zinc oxide layers on flexible ETFE films of about 100 micrometers thickness. And we use a different thickness of zinc oxide and silver. And by performing a very simple traction test of the direction of the arrows here, we find that there is two different regimes depending on the ratio thickness between silver and zinc oxide. When this ratio is low, you observe very long straight cracks that are parallel and perpendicular to the traction direction, and that goes through the wool sample. And if you have a high ratio of silver to zinc oxide, you observe very shorter cracks that are wavy. And if you look at the other direction, due to Poisson effect, you can observe a buckle for low ratio, and you observe wrinkle with no delamination, even at high strength. But in this presentation, I will focus on one observation, is that even at large strains, more than 10%, you observe a saturation of the fragment size, so the distance here, or the distance here, is nearly the same for both regimes, and this saturation is at a very large scale, so the order of 1 or 2 micron, whereas the thickness of the layer is of the order of 10 to 100 nanometers. So if you want to understand crack propagation in thin film, you can do an energy balance estimation between the cost to introduce a new crack in your system. So this cost is proportional to L to the square in a freestanding film. And if you compare this to the cost of creation of a new surface, which depends on the fracture toughness, the length of the crack, and the thickness of the system, you can find a classical result which tells you that there is a critical length scale in your systems over which the crack becomes unstable and will propagate in your system. And this length scale is simply the griffin length. So now if you put your thin film on a hard substrate, you will not be able to release energy on the same surface, so you will release it only on a square which length is L, and the other dimension is the thickness of the film. So if you look at this equation, you find that there is a critical thickness this time over which the crack becomes unstable and start to propagate in the system. And now if you are dealing with the case of thin film on soft substrate or soft substrate or flexible substrate,
You are in between those two cases, and you have to introduce a new length scale, which is the elastic discharge length scale, which depends on the modulus ratio times the thickness of the film, and the energy will be released in a region whose dimension is the length of the crack times this elastic discharge. So to illustrate this, the role of this elastic discharge, in 2000, Hutchinson and Zia proposed a very simple 2D elastic model to account for this problem. So they consider the substrate as a spring of a network of spring of stiffness K, and so they are able now to calculate the stress distribution at the surface of the film as a function of the normalized fragment length. So this time, big L is the time, is the size of the fragment, so the size of the blue part here in the drawing, and this is normalized by the elastic discharge length that I previously presented. So if you plot the normalized stress as a function of the size of the normalized size of the fragment, you can see that depending on this ratio, you can have a distribution that it's nearly flat over all the fragments, when the ratio of the size of the fragment over the elastic discharge length is high, which means that if you are now thinking about how to introduce a new crack in your system, you have nearly equal probability to introduce a crack nearly everywhere on your fragment. So crack can appear from here to here with equal probability. And now if you are at low ratio, so the stress distribution is like this, so there is a maximum at the middle of the fragment. So if a new crack is to appear, its probability is really higher to appear here. So you can illustrate it by making a very simple model macroscopic experiment. So you paint on the complement substrate either latex or ETFE to modify the length ratio. So if you put it on latex, this is the experiment of Evelyn Kolbs in 2002. You have a ratio that is close to 1, so the stress distribution is like this, so the probability to have a new crack in a fragment is higher in the middle, and you can see here that the first crack appears in the middle, then the other one just cut the fragment into segments of equal length. But if you do apply paint on ETFE, this time the ratio is very high, so it's about 100, so higher than the one that is drawn here, and you can see that cracks appear nearly everywhere in the sample with no specific place. So to get back to our first problem, we perform a traction test on zinc oxide, single zinc oxide layer deposit on flexible ETFE substrate, and we measure the crack spacing as a function of the strain. Here on this picture, I can see some new cracks that appears at the beginning in random places when the ratio of the crack length of the crack spacing is very high. And then there is a second regime which is characterized by this linear evolution of L as a function of the strain in the log plot. Where the position of the new crack is set by elastic interactions. That means that each fragment is cut into two new fragments of the same length. And then what is interesting is that we observe at high enough strain a saturation of this crack length, which depends on the thickness of the film, and which is of the order of some micrometer, whereas the thickness of the zinc oxide is of the order of the 100 nanometer for the iron. So if we try to understand this evolution of the crack spacing as a function of the strain, so here I plot the same data, but in a normalized plot. So all the curves follow the same master curves. we can try to use very simple models that are coming from literature, again from the paper of Xia and Hutchinson. So the first models they propose that all cracks propagate simultaneously. And this gives the red curves on this plot, so we can see that we underestimate the value of L, which is quite normal because this model is not physical, because it supposes that the cracks are able to get nearer and nearer as the strain increases. It's not physical at all. So they introduced a new model, which is a sequential model, in which they estimate the energy release rate needed for a new crack to appear in between two existing cracks. You can see, so this gives us the blue curves. So the estimation is better, but it's still incorrect, and we didn't succeed to capture the saturation of the crack spacing at high strain. So, in our opinion, we need to consider one more ingredient in those models. This is the plasticity in the substrate, which is not taken into account because all these models are purely elastics. Why do we think that plasticity occurs in the substrate? Because we have some experimental evidence. So we perform IFM measurement during the traction test, so in situ IFM measurement during traction test on the experiment I showed you just before. And here you can see that the crack opening as a function of the strain is linear, which is normal for an elastic system, but we can see that this opening depends on the history. There is a sort of memory effect. In fact, you see here a new crack appears, and its opening is far less than the previous one that is at the same strain. In fact, if everything was elastic, all the cracks should have the same opening, which is not the case. So we have here evidence of plasticity, which is localized from the substrate below the cracks. We have another evidence for this localized plasticity in the substrate, so we do a post-mortem IFM measurement, so this time there is no more strain applied to the sample, and we dip the sample in an acidic solution and this allows to remove only the coating. So here on this picture, on the left part, the coating is still here, but here the coating has disappeared. And as you can see, we still see the crack grooves. And if we do IFM measurement in this crack grooves, you can see that there is a groove in which was just below the previous position of the crack. So which means that this is only due to plasticity. The third and last evidence for localized plasticity is that we perform numerical simulation with cohesive zone models by introducing a random Tmax. So we use Gaussian distribution for Tmax in the field. And we observe plasticity that develops below the cracks. And at high strain, we see that the plastic region collapses, and we think that this collapse of the plastic region below the cracks is the reason for the saturation. And if you want to know a lot more about those numerical simulation, you can see 11 talk this afternoon in the same room, I think. So lastly, we propose a new model, so an extension of the Xia-Hutchinson approach that takes into account plasticity in the substrate, but we still have to confirm our calculation, but I plot here the result, and it seems to catch the saturation of the crackings. So I just showed you that crack spacing can be predicted once you take into account plasticity in the substrate, but as you can see in the study, there are many open questions mostly about what happened in the transverse direction due to pressure ratio. Why do we have some buckle with delamination on one case and some wrinkle with no delamination on the other case? Thank you for your attention.